So solubility depends on the interactive forces between solute molecules and solvent molecules, right? And this is that basis for likes dissolve likes, right? And so what do we mean by this? Another way to say it is that substances that have similar intermolecular forces can interact and form a solution. So substances with similar intermolecular forces can interact and form a solution. So, for example, if we were asked, would methanol form a solution with water, right? We would look at this and we would say methanol is polar, water is polar. They can also have hydrogen bonding, and so they will form a homogeneous solution. We might also be asked, would octane form a solution with water? Octane is a nonpolar solute. All it has is London dispersion forces. Water is a polar solvent. It's going to have London dispersion forces, but also hydrogen bonding and dipole-dipole interactions. And those hydrogen bonds and dipole-dipole interactions are going to be stronger than the London dispersion forces. So these molecules are more likely to stick together instead of interacting with the octane. And so you are not going to get a solution. And so sometimes we say, hey, look, this is immiscible. It means it does not mix, right? And so we can use our intermolecular force knowledge to be able to predict if things can form solutions. And so let's do an example of that in a second. I didn't skip one. No. Okay. Another kind of concept that you need to be aware of is, or just language really, is hydrophobic and hydrophilic molecules. Non-polar interactions, like dispersion forces, are called hydrophobic interactions. Hydrophobic means water-fearing. So these are interactions that repel water, and it diminishes water solubility. And these are non-polar interactions, like dispersion forces. Then you can have things that are hydrophilic, which are water-loving, and these are polar interactions, and they promote water solubility. So this is an interaction that attracts water, right? Like the polar interaction between OH groups in water. Right? And these promote water solubility. So one of the ways that soap works is that it has a nonpolar tail, but a ionized head here, which it will interact with polar molecules through ion-dipole interactions. And what happens is that means the soap interacts with the water, but dirt and oil are nonpolar, and so they get attracted here to the nonpolar tails. And so when you wash away the soap, you also wash away the dirt and the oil because they're trapped right here. And so you have some molecules that are both hydrophobic and hydrophilic, like soap molecules, which is kind of interesting. All right, now let's predict solubility in water. Consider the compounds carbon tetrachloride, ammonia, hydrogen fluoride, and oxygen, which should be very soluble in water and which should have limited solubility in water. Okay, the very first step is you need to figure out, are the molecules polar or nonpolar? If they're polar, they will mix and be soluble in water because water is polar. Okay, and so they should be able to mix like this. So that means we need to draw the Lewis structures to determine if they are polar. So let's do CCl4 first. Carbon is the least electronegative, so it's going to go in the center. I've already worked, just to help us with time, I've already worked these out. If you would like to calculate the valence electrons and review doing Lewis structures, you're more than welcome to. And if you run into a problem, pop by and see me. But I was just trying to save us time on this particular screencast. And these Lewis structures. And then we have O2. All right. So now we come through and we figure out if things are polar or nonpolar. There is a difference in electronegativity between the carbons and the chlorines, but this is a symmetrical molecule, so all of these are pulling in the same direction. So that sucker is going to be nonpolar. NH3 has electrons. It's a small molecule that has electrons on the central atom, so we know that is going to be polar. HF is also going to be polar. There's a difference in electronegativity there. And then O2, there is no difference in electronegativity between the oxygens, so it is nonpolar, right? So using this information, right, step 2, we can determine what should be soluble in water, and the polar things are going to be soluble. So NH3 and HF should be soluble in water. Okay. And so we can use Lewis structures and the polarity to figure out if things are water soluble or not. Now, let's talk about solubility and temperature for just a second, right? We know that if you have a solid in a liquid, right? Most of the time, not all the time, most of the time, if you increase the temperature, you increase the solubility. This is different for gases, right? When we talk about gases, right? If you have a gas and a liquid, if you increase the temperature, you decrease the solubility. And so let's look at an example here. Sodas are carbonated. And so we can see at a lower temperature, what's going to happen is there's going to be fewer molecules above the space. But then as we heat up the temperature, the molecules move faster. And there are more gas molecules above the soda. This is why sometimes sodas will explode in hot cars. So let's summarize that for just a second. At low temperature, All right. Gas dissolved in a liquid, which in this case is water, has less kinetic energy. Right? And so because it has less kinetic energy, right, we have induced dipole interactions between the solute and the solvent, and it keeps more gas dissolved. Then at a higher temperature, right, molecules have more kinetic energy, right, and that overcomes the solute solvent interactions and reduces solubility. And what that means is there's more pressure above the liquid. And so because there's more pressure above the liquid, it's more likely to explode. Now, we can also calculate this. So this quantitative relationship between gas solubility in a liquid can be related to the partial pressure. And so what we say then is, hey, look, the concentration of the gas, right, equals KH, which is a constant, times the pressure of the gas. And so the C of the gas here is just the concentration or solubility of a gas in a solvent, right? KH is just Henry's law constant, right? And that's specific for the gas in that solvent. And then P of the gas is the partial pressure. Of the gas in the environment surrounding the solvent. So if we look here at a soda, this is a soda and it's been canned under pressure and it has lots of CO2 here. And so when you open and release the pressure, the CO2 bubbles out, and that's because the gas is at a lower pressure. And so there's fewer gas molecules that are dissolved. At a higher pressure, there are more gas molecules dissolved. So let's look at an example using Henry's law. So we're going to calculate the concentration of carbon dioxide in a soft drink that was bottled under a partial pressure of 5 atm CO2 at 25 degrees Celsius. When you do this problem, you will also be given Henry's law constant for CO2. And so I just neglected to write it here apparently. 3.1 times 10 to the negative second moles over liters times ATM. Okay. And so we talk about to be able to solve for this, we need to use Henry's law. We know Henry's law equals C of the gas times Henry's law constant times the pressure of the gas. When we look at this, we're given the pressure of the gas. It's right here. We have Henry's law constant. And so all we need to do is plug those values in. And so to figure out the concentration of the gas, we come here and we say that's great. That's 3.1 times 10 to the negative second moles divided by liters times ATM. And then we multiply that by 5 ATM. When we do that, our ATMs cancel out and we're left with moles per liter, which is a concentration unit. And we're going to talk about that more in the next screencast. And so we've got 1.61 times 10 to the negative 1 moles per liter. And that's the concentration of CO2 in the soft drink. And so Henry's law can help us figure out the concentration of a gas in a liquid. If you have any questions, please feel free to stop by my office. In the next screencast, we'll look at some different types of concentration units.